Hi, and welcome to AMSC's Electrification and Grid Modernization for Future Loads, with me, Max the Superconductor. Since 2005, electricity consumption in the US has remained relatively stable, even though there are more ways to use energy than ever before. So why is that? It's primarily due to improved energy efficiency in the products we use every day, which has been really great for the environment. However, with soaring sales of electric vehicles like Tesla's, the power grid will experience unprecedented growth in electric loads. So if we look at electricity consumption again, here is the flattening from the energy-efficient products. But if we model for new loads caused by electric vehicles, they represent a huge disruption. So new electric loads are increasing, but the question is, how can utilities prepare for this new grid? Traditionally, for a new load of this size, a whole new substation would have to be built, which includes land acquisition, permitting, equipment, construction, and all of the disruption that causes. But we would like to introduce you to the magic of superconductor systems, or as we at AMSC call it, the Resilient Electric Grid, or just REG. REG systems allow utilities to network our existing power grid infrastructure, allowing for the distribution of electricity to be more flexible, safely managing emerging loads. Also, if aging or damaged equipment fails, that section of the grid can be backed up by connected substations, thereby increasing the entire system's reliability and resiliency. Also, REG systems are much more compact than conventional cables, which means much less disruption to the community. Going back to that urban example from before, REG systems could deliver large amounts of power in a manner that only requires a small substation be built, or avoid expansion of existing substations completely. Just think of what your community could do with all that extra green space. REG systems are much more attractive than conventional solutions in that they reduce or eliminate new substation costs, reduce construction required, simplify permitting, lower the overall project risk, and add reliability and resiliency to the grid by networking our infrastructure. Together, this results in less community disruption, while making REG-based solutions more economical. And there's so much more that REG can offer. Please visit us at amsc.com for all the exciting benefits of our resilient electric grid system. Just type in REG in the search bar on the homepage to start. Thank you for watching. I'll see you there.
Hello everyone, and welcome to Tech Talk Session 31. Today we will be talking about superconductor cable solutions and how they can be used to construct resilient electrical grids, or as AMSC calls it, REG, R-E-G, the acronym REG, R-E-G. So before we get going with the presentation, let's take care of some housekeeping things first. Questions, please put them into the chat box, and we'll get those answered at the end of today's presentation. Also, PDH contact hours. Remember to email myself or Matt, and we can get your certificate for your time spent today. And you can apply those PDH contact hours to your CEU credits that you need to maintain your engineering license. So today with us is Mike Ross of AMSC. Hi, Mike, and welcome to the show.
Hey, Paul. Thank you very much for the opportunity to talk to you. I really appreciate it. So my background is I've been with AMSC for 20 years. I'm an electrical engineer in power system planning. Over the years, I've had a number of roles over here at AMSC, but currently I'm the managing director of our superconductor power systems, which means our superconductor products for applications with the utilities and with industry. So just to get into the overview of what we're going to talk about today, I'd like to show you a little video kind of giving some of the main applications of superconductor cables in utility sectors, and we're going to focus on utilities today. So if you envision the way a typical utility is laid out in an urban area, so for example here we're seeing a typical downtown urban area, and the way it's set up is that you have a number of substations that are serving that urban area, and those substations are connected to the transmission grid. There's some reliability and redundancy built into the transmission grid, but there's no interconnections between substations at the distribution level. So if you do have an outage to any substation, you have a blackout. So one of the main applications of superconductor cables is to loop the substations together at the distribution side, so that if you do have transmission outages, you can move power around the urban area in these very, very high capacity cables that we'll talk about in more detail here shortly. So when we do that, we basically create a backup system to the transmission grid and create a very large increase in redundancy, and that in turn gives you more reliability and a greater level of resiliency in your projects in your downtown area. Another main application is that sometimes we do have load growth in urban areas where we need to build a new substation. And traditionally, the way that we might do that is we'd put in a new substation and we'd connect that substation to the transmission grid, usually with 2 or more transmission cables at transmission high voltage. And then we install a full substation with transformers and redundant components, a big control house, and so on. These are big projects, and they can be hundreds of millions of dollars in urban areas. So one alternative that this technology can bring is to be able to bring bulk power through superconductor cables to these new substations at distribution voltages. So at lower voltages, we're bringing power to the new substation, and as a result, you don't need to have as big of a substation. In fact, the substation can be about 25% the size of a typical full substation, which is much easier to site and far less expensive, far easier to permit, and that in turn creates lower cost overall projects in those scenarios where you do indeed have to build new substations in urban areas. So those are 2 main applications. One is increasing reliability, and another is increasing the ability to serve new loads. A third application of superconductor cables in urban areas is today the bulk of U.S. urban areas, the majority of them use something called pipe-type cables, or high-pressure fluid-filled cables, or oil-filled cables. Those are all terms for the same kind of cable. Here's a picture of what one of those looks like. So what we do in urban areas is we're putting these oil-filled cables in order to move bulk power around. And this is a technology that's becoming quite old. A lot of them have been around 40 or 50 years, and they're filled with oil that, if they leak, creates environmental hazards. The entire industry is moving away from this type of cable, and there's really only one vendor left in the U.S. that makes this type of cable. So utilities are trying to move away from it. So another application of superconductor cables is to replace these pipe type or oil-filled cables with superconductor cables, and we'll find that the installation of these cables and the coolant that's being used, which is liquid nitrogen, is far more environmentally friendly and minimizes the amount of civil works and disruption that would go into a project like replacing those pipe type cables. So those are the 3 main applications that we're gonna touch on today. Again, improving reliability in these loop type applications, improving load serving and capacity in the branch type applications, and then modernizing the grid. And what we like to say is that the combination of improving reliability, capacity, and bringing up things to modern technologies is how you create a resilient electric grid. Okay, so to take a big step back, let's talk a little bit about superconductor technology. So you may know that superconductors is a technology that allows you to move electricity with 0 resistance. And that's absolutely true. So this technology that we've developed can move power at zero resistance, so zero losses, very, very efficient. And that's kind of how people typically think of superconductors. But what I'd like you to think about is not only are we able to move power to very efficiently, but as a result of that, as a result of not having any losses, we can move power in a very, very compact manner. So energy density becomes very high in superconductor materials. And so that's what we're trying to show in this picture here in the top right-hand corner. Those handful of superconductor wires, so that silver wire in the top right-hand corner is the superconductor material, can move the same amount of current, the same amount of power as all of that copper. And the reason for that is because we're not generating heat when current passes through our material. We don't need to dissipate that heat. And the reason that you need all that bulk of copper to move a lot of current is because you need something to absorb the heat and it won't break down and melt. And that's why you need the large bulk of copper in order to move large amounts of current. Superconductors, all of that issue goes away, and you end up with these very, very high current dense wires that can move a large amounts of current. So if anything else that you get out of this presentation, I'd like you to think that superconductor material is a way to move power in a very small and compact way.
Hey Mike.
Now,
hey Mike, is
yeah.
there like a ratio for the current density in your superconducting cable versus that of the copper? Do you have a ratio at hand that you know of?
Yeah, we typically talk about a 200 times. So the cross-sectional area of copper has to be about 200 times larger than the cross-sectional area of the superconductor. And that's always improving. So as we continue to develop our processes and improve our wire, we can get more and more current in the same cross-sectional area. And that 200 times we expect will continue to become a larger and larger number as we can improve our current density.
Well, that's amazing, right? 200 times that's amazing. It's you're gonna be shipping bulk power with 10 gauge wire. It's amazing.
And that's really what drives the benefits and the value of this technology to utilities is that current density. In order to achieve that superconducting state that allows us to get that current density, though, there are some things that are needed, and the key one is that we have to cool the material. So we need to cool the material down to about minus 200 degrees Celsius. So very cold. That's the area where nitrogen is liquid. So that's we use liquid nitrogen to cool the cables. The beauty of liquid nitrogen is that it's really basically air. So 78% of what we're breathing is nitrogen. And when you turn that into a liquid, and then you use that liquid in our products, and then something happens and you spill it, it simply evaporates and becomes air. It's as environmentally friendly and non-hazardous a material as you could imagine, and that's a really great property. It's also very inexpensive. So companies like Praxair or Linde or Airgas or Air Liquide, these companies that manufacture and supply liquid gases, they're mainly after more valuable gases like liquid oxygen, argon, helium, hydrogen, those types of gases that make up a much smaller percentage of the atmosphere. But the process that they use to make those gases involves taking the air, pumping it down until it becomes a liquid, and then separating out those various liquids. And because there's so much nitrogen relative to the other kinds of gases, so for example, oxygen is about 20% of the air. So for every gallon of liquid oxygen you make, you end up with 4 gallons of liquid nitrogen. And they use the majority of it. So the food processing industry, frozen foods, are generally frozen using liquid nitrogen. The fishing industry uses a large amount of liquid nitrogen to flash freeze fish on the ships. Various industrial processes also use liquid nitrogen, but they're not able to sell all that they make. So a lot of liquid nitrogen becomes a waste product. So it's very inexpensive. It's about 50 cents a gallon on the bulk market. So it's an inexpensive and non-environmentally hazardous material that we're using as a coolant. And that really gives us a lot of advantages over existing technologies. Another factor that's important to know is that there is a critical limit. There's a critical current or a maximum amount of current that you can put through these wires. So each of those individual wires that we see in this picture can carry about 200 amps. If you try to push more than 200 amps through those wires, they stop being superconducting or they quench. So when we're making a power cable out of these wires, and we rate that power cable for 3,000 or 4,000 amps or whatever it might be, and then we use that power cable in a system, and then there's a fault on the system somewhere, so we try to drive 30,000 or 40,000 amps through that cable, it stops being superconducting. And what that means is it becomes resistive, and that transition from being superconducting, non-resistive, to being resistive adds impedance to the system that limits the amount of fault current through the cable. And that's a really important feature of this technology, because limiting fault current using conventional technology in utility grids is very challenging. And some of the applications that we're going to talk about really rely on that fault current limiting aspect of the cables to make the applications work. So we'll talk a little bit more about that.
Yeah. So Mike, which if you're transmitting more power and you have more capability, less resistance, it means your fault currents have gone up. A lot of times that equates to higher reliability, but there's always the concern with higher fault currents, the existing switchgear ratings that exist in these networks. This cable actually helps with that situation. It will potentially bring the fault currents down from where they currently are to lower levels, right, allowing the switchgear to continue to be used as they build out that system.
Right, that's exactly right. So the best way to think about it is that if you install a cable with a copper or aluminum cable, you generally see a fairly significant rise in fault current. So if you were to connect two substations together with a copper cable, you'll see a significant rise in the fault current level, which creates, as you say, protection challenges and fault current coordination challenges. But with the superconductor cables, because of this unique feature of fault current limiting, the rise in fault current is much lower than it would have been with a copper cable. And that allows us to do things with these cables that you could never do with copper cable.
I might add, those current limiting technologies that are used to limit fault currents, there's a couple manufacturers out there developing that have devices to limit fault current. They're quite expensive and oftentimes expendable devices within those within that equipment. Once there's a fault, they have to replace those items, and it comes at a pretty high cost.
Yeah, that's exactly right. Most of the technologies being used are we call them explosive fuse technologies, where when they operate to limit fault current, there's a component that blows up and limits the fault current, and then that component needs to be replaced. There's the use of explosives that need to be handled properly. There's a lot of training involved, a lot of storage requirements involved. With this technology, it limits the fault current, and then when the fault goes away, it goes back to being superconducting with no interaction between the operators or people in the field. It just naturally has that characteristic as part of the physics of the technology. So when we take this material and we make power cables, so those cables, as a result of using superconductor wire, have some interesting characteristics. So the first thing is that there's very high power transfer capability in these cables. A typical power cable, the largest that you can buy, can handle about 1,000 amps. It's very difficult to find a power cable for utility applications that can handle more than 1,000 amps once it's installed and operating. Our cables can handle about 4,000 amps in their maximum design. And the only reason that we limit ourselves to 4,000 amps is that we still have to connect to the existing grid, and that existing grid is going to use conventional equipment like breakers and bus bars. And it's almost impossible to buy breakers and bus bars and other equipment that's rated at more than 4,000 amps. So while we can move huge amounts of current through our cables, we usually limit ourselves to what ancillary equipment we can buy, which is about 4,000 amps. But it's still 4 times what conventional cables can move. Additionally, when you install a conventional copper or aluminum conventional cable in a utility grid, there's a lot of requirements associated with getting the heat away from those cables. So anytime you run electricity through any copper or aluminum device, it's going to generate heat. And if that heat's not able to dissipate, eventually the device will break down and fail. So there's a lot of effort when utilities are installing power cables to make sure that heat dissipation is sorted out. So you can't bury the cables too deep underground. You can't put cables too close to each other. All sorts of rules and requirements are needed in order to avoid this heat issue. With superconductor cables, we're cooling the cables internally with this liquid nitrogen. And what that means is there's no heat exchange with the outside world. The cables can be put very deep underground without any need to derate them. You can put multiple cables together, very close together. You can put them next to steam pipes or other power cables that are already in the grid, and it won't be impacted by the heat coming from those cables, and it won't create heat that will impact the existing equipment. And that is a very big deal when it comes to how to site these cables. And we'll see soon what that does is gives the utility engineers options to make more direct cable runs. You can use installation techniques like directional drilling, where instead of ripping up the streets and installing a cable and interrupting traffic and having all the civil works required there, you can simply horizontally directional drill and avoid those types of issues. So those are 2 incredibly important characteristics of these cables that differentiate them from copper cables. We already talked also about the fault current limiting, and we'll talk a little bit more about that. And then the 4th thing that makes them different is magnetic fields. These cables have no EMF around them. So there's a lot of perceived health implications of EMF around electric equipment. When people put in new power cables or new overhead lines, there's often a lot of community opposition because of concerns about how those electromagnetic fields will affect people's health. And then there's other concerns as well. For example, if you put a power cable, a conventional transmission cable, near something made out of metal, like a bridge or railroad tracks, the magnetic fields from the power cable will cause current to flow in those metal components, which causes heating and other problems. So very often you're not allowed to put power cables, transmission cables, on bridges and in other locations because of that issue. With superconductor cables, again, that problem completely goes away. So you can now put the cables in places, again, where you can't put conventional cables. And this idea of being able to put these cables and site them where previously you couldn't is one of the big value applications of the technology. Just to talk a little bit more about the fault current limiting aspects of the cables. So the wire itself that I was showing you before that can carry 200 amps in that little wire is really only 1% superconductor material. So superconductor material is a sort of ceramic material. Like a coffee cup kind of material. So it's breakable, it's delicate. So we had the same challenge that the fiber optic industry had. How do you take a material that's inherently brittle, like glass, and turn it into a cable that can be bent and pulled and twisted and buried underground for 40 years without damage? And the trick is that you make that brittle material very thin, and then you coat it with a stabilizing layer, a mechanical stabilizer. So in the fiber optic industry, they take the glass fibers, they make them very thin, and then they coat them with plastic. And the plastic gives them the mechanical strength. With superconductors, we take that superconductor layer, we make it very thin, it's about 1.2 microns thick, and then we coat it with other metals, copper, brass, stainless steel. We have a lot of options that we can use. So when you end up with a final wire, it's 99% copper, brass, or stainless steel, and only 1% of the superconductor material. Copper, brass, and stainless steel have resistance. So what we're seeing in this picture here is normal operation. Current runs through the wire, and all of the current runs through that very, very thin superconductor layer when we're superconducting in the normal conditions. So none of the current runs through the copper, brass, or stainless steel. But when there's a fault on the system and you try to drive high current through the wire, the superconductor layer stops being superconducting and pushes the current into those other metals. And that creates resistance, that creates impedance, and that limits the fault current. And we can control that to a certain degree by choosing. Copper is relatively low resistance, stainless steel is relatively high resistance, and brass is somewhere in the middle. And then there's thicknesses and widths that we can adjust to further fine-tune the impedance. So with that's kind of the way that we create the fault current limiting aspects of the material. So we have these cables now, and the cables have these very unique characteristics. Very high power transfer capability, basically zero resistance, no EMF, no thermal constraints for placing, no heat exchange, and this fault current management. So they physically look like conventional cables. That's in the top left-hand corner. No expert in power cables would ever know that that's a superconductor cable and not a conventional cable. They look exactly the same. The cables can be spliced. So we get about 15 to 1600 feet on a cable, on a standard cable reel, and then you splice those cables together to get to whatever length that you want, as you would with any conventional cable. Pulling strengths, bending radiuses are similar or better than conventional cable as you're pulling through ducts. You can pull them through ducts, or you can direct bury the cables. You can lay them in trench. Any way that you would install a conventional cable, you can install these cables. The biggest difference is, of course, the liquid nitrogen cooling system. And even that's really not so different than things that we do today. So I had mentioned earlier about those oil-filled cables or pipe-type cables. In about 30 or 40% of those applications, the utility will circulate oil through those cables. So the oil will flow through the cable, will pick heat up off of the cable, and then somewhere in a substation, there's a heat exchanger that the hot oil flows in, the heat's removed, and then cool oil is flowing back through the cable. That's exactly what we do to cool our superconductor cables, but we do it at a much lower temperature and with a much safer and more environmentally friendly material, liquid nitrogen instead of mineral oil.
Mike, what is that temperature that you're...
Yeah, minus 200 degrees Celsius or 68 degrees Kelvin is the temperature that we operate at. So it's very cold, but again, the liquid nitrogen is a material that's able to operate at those temperatures and is very inexpensive and very plentiful. This slide is showing the main configurations of superconductor cables. So at AMSC, we supply a wide variety of cables. On the low voltage side, we have a variety of cables that can operate at 1,000 volts or below for industrial applications and military applications. So we have three-phase AC cables. Those can be used in places that are using high current AC. So there's facilities that use 120 volt or 480 volt AC at very high currents, aluminum smelting, water treatment, water desalination, and many other industries use very, very high current, low voltage cables. In low voltage DC cables, that's commonly used in the data center world, where you're moving 48 volt DC, very large currents around a data center. Superconductor cables can replace those very large current cables. On the right-hand side here are the configurations that we use for utilities. The three-phase AC concentric phase cable is the most commonly used cable that we're looking at now. This is the design. So what you're looking at here is a three-phase cable. So phase A, B, and C are all concentrically wound in a single cable. So this is very different than what you can do with copper. What that means is that you can have all three phases in a single cable, and each of those phases can be up to 4,000 amps. So you get almost up to 12,000 amps can be passed through this cable, or 4,000 three-phase. So what that means is that this single cable can replace up to 12. Remember, a conventional copper cable can only handle about 1,000 amps. So if you have 4,000 amps times three phases, that's 12 cables that are replaced by this one single cable. And those 12 cables, they can't be right next to each other. They have to be spaced out by several feet. So you can imagine that a conventional cable system to move the same amount of current that this cable system can use would be in a duct bank that would be a couple of feet, 2 by 3 feet minimum, and in a lot of cases a lot larger. And we can replace all of that with a single cable that's about 10 inches in diameter. So that's the main advantage. Just giving you an idea of the main advantages of this technology. What we're looking at here is two different cables by two different manufacturers. The top one is from Southwire. The lower one is from Nexans. In both cases, these they're using American superconductor material. You can see that the configurations are generally the same with some differences. So what we're looking at here is a cable that goes inside what we call a cryostat. So on the right-hand side, you can see you have a cryostat, which is a double-walled stainless steel tube, and between those two walls is a vacuum. So just like your travel coffee mug, if you have a stainless steel travel coffee mug, that's the same concept. You have two layers of steel with a vacuum in between, and that vacuum creates the thermal insulation for us to move our cold liquid nitrogen through the cable. And you can see we can run liquid nitrogen down the center of the cable or around the outside of the cable in order to keep it cold while not losing very much heat because of this cryostat on the outside.
Hey Mike, what's the voltage of that cable?
This particular cable is good up to about 36 kV. When we get beyond 36 kV, we have to move to different designs. And that's because the electrical insulation from phase to phase gets too thick at some point, and you can't meet your bending radiuses anymore. So once we get to 69 kV, we move to what we call 3-in-1, which is this center design. So you have three single-phase cables in a single cryostat. So that's good for 69 kV and some 115 kV applications. But then when we get to transmission cables, 115 kV and above, we go to separate cables in separate cryostats. So you have single phase cables as you would, looks a little bit more like a conventional design. And I'll show some real life applications of all of these designs. So we talked a little bit about cryostats and what that is. And again, those cryostats is a technology that's much larger than superconductor cables. So the industry buys a lot of what they call vacuum jacketed pipes from various manufacturers to move very hot or very cold liquids and gases around factories and other applications. So this is a technology that's been around about 40 years, available from many suppliers. And we take that existing, very mature technology and put our cable inside that. The cryostats are flexible. They're corrugated, as you can see, so you can bend them, and they fit on standard utility cable reels with no problem whatsoever. They're very tough. They're made of stainless steel and so on. So you have a sidewall pressure strength or a crushing strength that's about 10 times stronger than the most commonly used utility cables today. And so what that means is that these cables can be pulled much harder. They can go around corners much better than conventional cables. Additionally, because there's all this stainless steel in these cryostats, you essentially have, from a safety perspective, a double-walled conduit. So in the event that someone dug into the cable there was some kind of fault in the cable, you have all of this grounded metal around your power cable that the electricity can be grounded into, which makes it less likely that whoever is running the backhoe that dug up the cable or whatever will be injured by the electricity in the cable. Cooling systems are another really important part of these projects. So we talked a little bit about how we have to keep the cables cold. So there's two main technologies. There's open loop cooling systems and closed loop cooling systems. Open loop is usually more attractive to our industrial customers. And basically what you have is a big tank. You rent that tank from a supplier like Airgas or Praxair or Linde or someone like that. And they come along and keep the tank full of liquid nitrogen. And then we consume that liquid nitrogen to keep the cable cold. So we basically absorb the liquid nitrogen, or we draw the liquid nitrogen out of the tank. We use that to cool our cable. And then the supplier of the liquid nitrogen periodically comes around and fills that tank back up. The attractiveness of this approach is that it's very low initial cost. There's very little equipment. There's very little maintenance. There's aside from a pump, you really have no moving parts, and you're not using very much electricity to cool the cable. The downside of this approach is that you need to find a place to install that liquid nitrogen tank, and you need to fill it periodically. So for urban utilities that have very tight substations and don't have a lot of space, this isn't attractive. So that's when we go to what we call a closed loop system. And in that case, we have a refrigerator. So this slide is showing a very large refrigerator. This refrigerator is able to cool about 5 miles of superconductor cable. There are many technologies available, different sizes, different shapes, different cost points, different maintenance requirements that can be used to cool the cables. And in this case, you don't need a big tank. You don't need regular deliveries of liquid nitrogen, but you do connect into the auxiliary power. So you basically are using electricity to cool the cable instead of consuming a liquid nitrogen. And for utilities, electricity is very plentiful and inexpensive for utilities. So their preference is usually to use this type of approach.
So Mike, that closed loop system, is that a refrigeration system basically also, or?
Yeah, yep. We call it a cryo cooler, which is a refrigerator that's operating at these low temperatures that we're talking about, minus 200 degrees Celsius.
In the open loop, you're venting to the air, so you're getting your cooling through the expansion process of the nitrogen, I assume. Is that what's going on?
Yeah, there's different ways to do it, but yes, basically the liquid nitrogen is consumed, it becomes a gas, and then it's just released to the atmosphere, because 78% of the atmosphere is nitrogen, and that's not a problem. The final major component of the systems is the terminations. So the terminations is where you transition from the conventional grid into the superconductor cable. In the middle here, and I've got a better slide of this coming up, is the original termination. This was installed in 2006 at AEP, a utility in Ohio, as a demonstration project. And so what you can see is that there are 3 phases coming in. So phase A, phase B, and phase C are dropping down into the termination in our single superconductor cable. This is 13.8 kV, comes out the end. So this was the original prototype. We learned, that this was a bit large. We were able to demonstrate the technology, which was fantastic. It's a bit large for practical applications. So over the years, we've now developed a much more compact, modern termination, which is what we're seeing here. So in this termination, again, you have phase A, phase B, and phase C coming into the termination, and the power cable comes out the end. This is designed to be installed in metal-clad switchgear or typical utility cabinets, and therefore it's very compact and very easy to install. This is for distribution voltages up to 36 kV. When you go to transmission voltages, 69 kV and above, often we're using single phase terminations. So these are what you're looking at here. This is 138 kV terminations. And I have another slide that looks a little bit closer to at this. So those are the main components of the system. So talking about applications. So what is the value of this technology to utilities? And the main value is, again, this power density. And so at a given voltage level, so say you have a 138 kV superconductor cable, we already talked about how that can carry about 4 times as much power as conventional technology. So the typical cables that people are installed today are called XLPE cables, or extruded dielectric cables. So we can do about 4 times the power at a given voltage level. But where we really see value is being able to move the same amount of power that a transmission voltage cable can move at distribution voltages. So we can lower the voltage, but still have the same power. And this is where we really see major value for especially urban utilities. If they could move bulk power around their grids at distribution voltages, there's a tremendous amount of value that can be saved by not having to install large, expensive transmission equipment in urban areas. So we'll talk more about that. Also, the siting advantages of the technology. So we talked about this a lot already. We can put them deep underground. They don't generate heat. A lot of things that you can't do with conventional cables. And that's important because when you tear up the streets in most urban areas, this is Manhattan, but this looks the same in many urban cities. You pull up the streets, and there are many, many different conduits. Some of these are phone, internet, water, sewer, electricity, steam. All sorts of things are going on underneath the streets. And to put a new power cable in this area using conventional technology is really difficult, because you have to make a study that determines how your power cable that you're installing is going to be affected by all these different components, and how the new heat that you're going to add, because your power cable is going to generate heat under the streets, so they're going to impact all of these things. So it's a very complicated study, and a lot of times you simply can't install the cable. And that means you have to go a different way around this mess to get to where you're going. So you're doing longer runs, more complicated paths, more complicated routes than you would do if you had a technology like superconductor cables, where you could install it and not have to worry at all about the new cable being affected by these things and the cable affecting these things. Also, as I mentioned before, you can simply directionally drill underneath this mess and avoid the whole thing, avoid opening up the streets. And that is a huge value to utilities. This other slide is just representing what I mentioned before about a single superconductor cable replacing 12 conventional cables. And again, as you think about how busy the streets are, you can quickly see how this is really advantageous to utilities. A little bit of history. So this is the first superconductor cable that's using this concentric phase design, was demonstrated in the US. I mentioned this before. This was in 2006 with AEP in Ohio. This was part of a program by the Department of Energy to demonstrate superconductor cables, 13.8 kV, 60 MVA. This was installed and operated for 4 years. After 4 years, we took it apart, we chopped up the cable, we looked for any degradation. We wanted to make sure that the cable was operating and would operate for 40 to 50 years with no problems, and the entire project was incredibly successful. So this was the first demonstration, getting to be 15 years ago, where we first demonstrated this technology in a US substation at distribution voltage. 2 years later, in 2008, we demonstrated 138 kV, a transmission voltage at LIPA in Long Island in New York. Again, part of the Department of Energy program to demonstrate this technology. This was a 574 megawatt cable. And just to give you an idea of why this technology is attractive, in this single 2 meter wide underground corridor, we were able to move the same amount of power as this 70-meter wide overhead corridor. And with today's typical public opposition to overhead lines, it's very difficult to install a new overhead line because people don't want to look at the power cable overhead lines. This is a major technology advancement and something that we think is going to be very, very attractive as time goes on, and it becomes even more difficult to build new transmission lines. Want to talk a little bit about the first permanent installation of superconductor cables in the West, in Europe or North America. So this project was in Germany. It's called the AMSC project. It's in Essen, which is near Cologne in northern Germany. This was installed in 2014, has been operating with 100% availability ever since. It's a permanent part of the grid. The application is that you had a downtown substation called Del Bruges. This is a European city that has the typical pedestrian core, so all of the utilities are underground. And then they had a problem where the city was growing and they needed to add more power to this substation. And the way they would normally do that is they would bring a 110 kV transmission cable from the suburbs into the new station and then install a 110 to 10 kV transformer, and then you would increase the power capacity of the substation in that way. But there was no room. It's an underground substation. There's no place to put a great big 110 to 10 kV transformer. So what they did instead is they put the new transformer out in the suburbs where you had plenty of room, and then brought the power in using a 10 kV superconductor cable, 2300 amps, 40 MVA, into the substation. And now they were able to increase the capacity of the substation by 40 MVA just by adding in a new switchgear cubicle and a new termination for the superconductor cable. So much smaller. So they were able to avoid expanding a underground urban substation because of this technology. And that's why this is so attractive. Here's a couple of pictures from this project. So this is the type testing of the cable. So every cable, superconductor cable today is a bit different. We haven't hit the point yet where we're making the same cable over and over again. So we run a lot of tests because each design is new, called type tests. And a type test involves a 40-meter cable, 2 terminations, and a splice. And so this is installed inside this test chamber, and then a whole battery of tests are run on the cables. So there's standards exist in IEC and CGRE for the testing of superconductor cables. And so those are standards that the utilities run down, and they explain how to test the cables in order to prove that the design is going to work properly. So this is done for every cable today. Here's the cable being installed. So again, this is a conventional cable rig. This is a conventional cable reel. The crew is a crew that would be the exact same skill sets that would be used to install any cable. And this is them pulling the cable into place. Here's the termination. This installation was set up so that people could visit the substation and see the installation. So they elected to put the termination in a way that's visible with this cage around it, so people can walk in and look at it. But this is the basic idea of the termination of the cable. So you can imagine this termination orientated vertically and put inside a cabinet, and that's what we're doing in other projects. Here's where the splice for the cable would be installed. So the splice does require specialized labor. So the manufacturer of the cable, in this case Nexans, also provide the labor to do the splice. And what they do is they have this shipping container that has no bottom, and they put that over the place where you're going to do the splice, and then they do the work so they're outside of the elements. And then they just go ahead and pave right over the splice box. The reason that they're allowed to pave over the splice box in superconductor cables is that unlike conventional cables, you don't need to inspect these cables periodically. You can simply bury them and keep them operating. With conventional cables, they heat up and cool down every day. So when more current flows through the cables, they heat up and they expand a little bit. And then at night, when the load drops off, they cool off and they shrink a little bit. And that, over the years, that expansion and contraction eventually causes terminations and splices to fail. And so utilities have to annually inspect their splices and terminations. With superconductor cables, once they're installed and operating, their temperature never changes, regardless of how much current's going through them. There's no expansion, there's no contraction, there's no need to regularly inspect the cables. So the manufacturer of the cable recommends just going ahead and paving over the splice box and keeping the splice out of the elements. So it's a very interesting aspect of the cable. Now I'd like to talk to you about a North American application study that we did in Boston with Eversource, NSTAR at the time. So this is a project that's very typical of the types of studies that we do today. So downtown Boston, like most utilities, is broken up into various segments, and those segments are each served by a substation that's interconnected at the transmission side with various redundancies. But at the distribution level, there's no interconnections between these different regions. So like that video that I showed earlier, if they were to lose all of the transmission or transformation to any one of these substations, you'd have a blackout. In 2012, there was a major fire at a substation in the Back Bay of Boston that had that happen. All of the transmission and transformation into that substation was lost. And so you had a blackout of the Back Bay of Boston. What the utility had to do was run power cables through the streets in order to jumper together the grid that went down to the other grids that were still had power. So you had 8 different jumpers were run through the streets in order to basically rewire the grid so that they could continue to serve load. It was an amazing achievement. It was an emergency achievement. They managed to do this in 2 days. They were able to jumper things together. But it was obviously a very a difficult thing to do and something they never want to do again. So that's when the concept of a superconducting loop or ring was invented, where you would interconnect substations together at the distribution side using superconductor cables, so that you're basically duplicating this work that the utility had to do, but you do it in a way that's permanent and that's not so disruptive to the outside world. And that's this idea of the superconducting ring for resilience and reliability. Our customer, NSTAR, now Eversource, did a study at the time where they looked at conventionally how could they get the same level of reliability as the superconductor solution using conventional technology. And they came up with $130 to $155 million to do a project like that. So as an alternative, we proposed doing superconductor cables. There's about 5 miles worth of cables in 3 segments that would basically duplicate those jumpers that they installed over the streets, but now we're talking about doing it underground. Our cost to do the project like that was about 2/3 the traditional cost. So this was a very attractive proposal for the utility. However, right at that time was when NSTAR, the utility that served Boston, merged and became the utility that we know today as Eversource. And so at that time during the merger, they were unable to do a major project like this. So we took this concept and we brought it over to Chicago. And right now, today, we are installing a very similar project in Chicago with ComEd as we speak. The project in Chicago is very, very similar. One of the complications in Chicago is that they have multiple transmission voltages. So there's 69 kV, 138 kV, 34.5 kV being served these various utilities in Chicago. So if you were to try to connect these substations together at transmission, it's very difficult because they're at different voltages. So you need big power transformers and things like that. And like any urban utility, Chicago doesn't have a lot of room for equipment like that. So this concept of connecting the substations together at the distribution level is hugely attractive. The basic project that we're executing in Chicago, the phase 2 of the project, will involve interconnecting 3 substations together. 2 of those substations are at 69 kV and 1 is at 138 kV. When we loop those substations together, we'll be able to bring the reliability level of downtown Chicago up from its current level of N-2 to N-3. So what that means is today, they can lose any 2 transmission components and still be able to serve their load. But when the system's installed, they'll be able to lose 3 components, so an entire another level of redundancy without losing power. And that's what resiliency is all about, increasing the reliability so that you can lose larger components of the system without having a blackout. Now, what ComEd asked of us is that they have this reliability increase, but without any new high voltage transformers, without any new infrastructure construction, and absolutely no expansion of their existing substations. So here's another look at the project. You have 2 substations, Dearborn and Plymouth Court. They are connected radially to the grid at 69 kV, which means that there is some redundancy. So there's 4 circuits of 69 kV here, but there's an opportunity for an outage if you have an outage in this circuit. State, however, is a much more reliable substation. It's got multiple sources to it. So by interconnecting these 3 substations together with a superconductor cable, we can increase the reliability of all of these substations in the event you lost the traditional service. Before we get into that big project, we're installing a phase 1 of the project at a substation nearby, where we're showing ComEd how this project will be installed in the downtown area. So we're doing all the things that we would do in the downtown area, but in a smaller project within a substation. So this is an idea of that project. So what we're doing is we're connecting different sides of the substation together with a superconductor cable. Same voltage, same rating, same terminations, same splices as the main project, but at a smaller scale, so that ComEd can demonstrate the technology and get comfortable with it before it gets deployed in their downtown area. So this project is under construction today, and we, I think, are likely to have a future tech talk with ComEd to talk about more details of this particular project. So I wanted to talk just a bit about one important aspect of the ComEd project, and that has to do with how the project is treated from the utility's perspective as a transmission asset rather than as a distribution asset. So when utilities install their projects at medium voltage or at distribution voltage, it goes through a process where they install the equipment, and then later they go to their regulator, the state regulator, and ask for a recovery for that expenditure or that investment from the ratepayers of the area. So they have to install the technology, pay for it, and then later get the recovery for that technology. On the transmission side, it's different. They first go in and they get approval from the national regulator, the FERC, the Federal Energy Regulatory Commission, and they go in and they get approval ahead of time for the project. And then once the project is installed, they automatically get recovery for that project, or they get their investment returned to them for that project. So as a result, it's a lot more attractive for utilities to do transmission projects than distribution projects. But as we talked about before, this technology is being operated at distribution voltage. So you normally would think of it as a distribution technology, but it's really serving a transmission purpose. We're replacing transmission circuits. So as part of this project, ComEd filed with FERC and asked them to treat the superconductor distribution voltage cable as though it was a transmission asset. And in this filing, they talked a lot about why they want to put in the cable. So I just wanted to point out a couple of things that were in this filing that ComEd made to FERC about the project. So today I talked about how superconductor cables, resilient electric grid cables, are easier to site and install. So in ComEd's legal filing to FERC, they stated that this technology was far less disruptive to their downtown core area. Similarly, today I told you about how superconductor cables have smaller installation requirements and smaller substation requirements. And in FERC's, the ComEd's filing to FERC, they said that this project with superconductor cable will not require significant infrastructure construction. So kind of showing that statement is true. We talked today about how these superconductor cables provide transmission power, but at distribution voltage. So ComEd's filing talked about how transmission, the cable is a transmission facility serving a transmission function, even though it's at distribution voltages. And then, of course, I've been implying today that these superconductor cables at the overall projects are ultimately less costly than conventional projects because of these things that we're talking about. And in ComEd's FERC filing, they state that the whole overall project will be tens of millions of dollars less cost to the ratepayers of the area. So in this filing, ComEd is saying to FERC all of the things that I've been saying to you. On May 28th of last year, FERC approved the project and demonstrating that all of those statements that we're saying were agreed to by the main regulator of the utility industry. So what that means is that superconductor cables are now a proven and accepted technology for utility applications. That's the result of a utility that in a bellwether American city has shown that the value proposition I talked to today is true. That the precedent of this filing shows that superconductor cables at resilient electric grids can be used for grid resiliency, and that resiliency can be recovered as transmission assets. And another aspect of that filing had to do with risk management. Because FERC approved the project, the technology risk or anything that people might be concerned about the newness of this technology is shifted off of the utility because of this approval. So the technical risk has been retired on the technology from the utility's perspective. So just to conclude the presentation, superconductor cables have many benefits over conventional cables, particularly in urban areas. You can think of superconductor cables as alternatives to transmission cables, transmission power at distribution voltages. The main applications are capacity increases, like what they did in Germany, reliability increases, like they are doing in Chicago, or by modernization and moving away from older technologies like pipe-type cables. Superconductor cables can be lower cost than conventional cables, and I want to make it clear that this ruling that FERC had about superconductor cables and that can be treated as a transmission asset is a very important part of the project. So that's my presentation, and now I'd be happy to take any questions from the audience.
Great. So we got a bit of an echo. So anyways, Mike, thank you very much. And we're going to jump over to a question screen for a moment, and then we're going to come back with the list of questions for you, if you don't mind.
Very good. Thank you.
Okay, we're back with you. So a lot of questions. I think it's a record for the number of questions. So thank you for the questions. But before we get on with the questions with Mike, I want to first state that the PDH certificate code, to get the code 543, so 543, send an email to myself or to Matt and we'll get you that certificate. We appreciate you guys coming on to listen to these Tech Talks. Also, don't forget what NEPSI does. NEPSI manufactures metal closed capacitor banks, harmonic filter banks at the medium voltage level for reactive compensation. AMSC, our parent company, produces STATCOM technology for reactive compensation. It's a dynamic reactive compensation solution. And because now we're joined at the hip, we are also supplying what I would call hybrid STATCOM reactive compensation solutions, so we can extend the STATCOM technology. And let's not forget what Mike had talked about today, superconducting cable technology applications, and that is also available for you guys. So Mike, we have lots of questions. I think maybe the easiest thing for you to do is just to read through the questions starting at the top and answer as you go.
Sure, no problem at all. So I'll start at the top here. There's a question about nitrogen. Is it dangerous if it leaks into an enclosed personal space? Yeah, so the worst thing you can say about nitrogen is that it's not oxygen. So there is a suffocation risk if there's a leak in a piece of refrigeration equipment in an enclosed space. But utilities are familiar with that sort of scenario. So most utilities have a carbon dioxide or halon fire suppression system in their substations that are used to suppress fires. And as part of that, you have oxygen sensors and oxygen alarms. So in the event that the oxygen level in an enclosed space drops down, you have an alarm that warns any personnel that they need to get out of that area. So the same sort of approach is used for places where superconductors are installed. The next question is about helium, liquid helium for cooling. So liquid helium is actually operates at a much lower temperature. Liquid nitrogen is good down to, we operate at 68 degrees Kelvin. I think liquid nitrogen at a high enough pressure can be a liquid down to 65 or 64 degrees Kelvin. Liquid helium is down to 4 degrees Kelvin, very, very cold. And liquid helium was actually used for cooling in what we call low temperature superconductors, or the original superconductor technologies discovered in the 20s, I think, that is currently used today in MRIs and other medical imaging approaches. So when you put your body in an MRI machine, what you're doing is you're putting your body in a coil of low temperature superconductors that's being cooled by liquid helium at 4 degrees Kelvin, and that's the main application of low temperature superconductors. What we're talking about with this technology is high temperature superconductors. Relatively high temperature, 68 degrees Kelvin instead of 4 degrees Kelvin, and that's where we can use the liquid nitrogen. The problem with liquid helium is it's very, very expensive. Liquid helium is a very rare element, and at least on Earth, and is quite expensive. So it's not practical to do power cables cooled by liquid helium. In some of our other applications, we do use gaseous helium for cooling, but liquid nitrogen is the most cost-effective cooling medium. As far as the cost difference between superconductors and a regular conductor, superconductor cables are quite a bit more expensive. We look at things on a project level. So what you're trying to do is solve a problem in the most cost-effective way possible. And if that approach can involve avoiding the expansion or the construction of a new substation, avoid the placement of a large power transformer in an urban area, avoid major civil works, ripping up the streets and so on, then the overall project can be cost-effective, even if the superconductor cables are quite a bit more. A big part of what American Superconductor does, or AMSC does, is we have a group that studies challenges that our utility customers have and puts together proposals and study work to show how this technology can be more cost-effective relative to other technologies. and that's how we evaluate those projects. Yes, do the cables require special cable joints and terminations? And the answer is yes, and they are different from conventional cables. Let's see, there's a question here about the cryogenic cooling plants, and is that the limiting element? I wouldn't say that necessarily. We can put in multiple cryogenic cooling plants. In general, we say that one cryogenic cooling plant can handle about 5 miles, 10 miles or so of superconductor cable. It depends on a lot of factors, elevation changes, the diameter of the cables, and things like that. It's really a fluid dynamics problem. So you're pumping liquid nitrogen through the cables. You have to be able to keep your head pressures within reasonable levels and that sort of thing. So if you're going to go longer than those amounts, you simply need another pumping station, another cooling station at another location. So I wouldn't describe the cryogenic cooling plants as the limiting element in cables.
Hey, Mike, maybe I interrupt 1 second, and I noticed the question is by Rusty Bascom. So, Rusty, how you doing? It's been about 15 or 20 years since I talked to Rusty, but Rusty Bascom worked for PTI back in the 90s with me, and also went to RPI. So, hi, Rusty. Thank you for coming on the show. Rusty Bascom is an expert in cables. He's been doing cables, I think, for his entire professional career out of Phoenix, Arizona. He works for Electrical Consulting Engineers. So, thanks for coming on.
Thank you for joining us, Rusty. ECI makes or PTI makes the PSSE modeling software program that we use extensively to model these power systems. At any rate, so the question is about he's pushing back against my contention that 1,000 amps is the most that you get out of a conventional cable, and yes, I won't doubt, Rusty, that there are cables out there that can do larger amounts of current. However, you do have to keep in mind that you do still need to get the heat away from those cables. So even a 2,000 amp cable, if you put it too deep underground and you don't have the appropriate thermal backfill or other characteristics installing the cable to make sure that the heat can be dissipated, that current rating will be derated. Superconductor cables, you can do whatever you like with them in terms of siting, and they'll never be derated. And that's kind of the distinction that we're trying to make. Is there a design of the superconductor that is air-cooled or doesn't require supercooled liquids? So no, the superconductor technology out there today that operates at kind of normal pressures do require cryogenic temperatures and supercooled liquids. I've seen some science articles out there about materials that under incredibly high pressures can hold superconducting characteristics at nominal temperatures, at room temperatures, but those things aren't practical at this stage. Hopefully someday there will be room temperature superconductors, but we certainly aren't there yet. The next question is about the technical readiness level of superconductor technology. So at medium voltage, especially 15 kV, we are at TRL 9, fully technically ready. That's what was demonstrated in the project in Germany that we talked about. And we are commercially selling medium voltage superconductor cables. The transmission cables, one could make an argument that they're closer to TRL 8 and possibly TRL 7, more likely TRL 8. In Korea, LS Cable and KEPCO, the utility in Korea, have installed 154 kV superconductor cables in a couple of different scenarios that one could possibly argue that those are at TRL 9, but I think more practically one would say transmissions at TRL 8. How is the increase in losses?
Mike,
yes.
If you don't mind me asking, what does TRL 8? What does the
technical readiness level? So that's a common scale that's used. I think TRL 1 would be saying that there's a theory that something could work, and then you move up the stages. I think TRL7 is that a demonstration project in a real world environment has been performed. TRL8 I think means that that the technology is ready to be marketed but hasn't been installed commercially, and then TRL9 is fully commercialized.
Okay.
So that's that question. Let's see. So the basic question here is when there's a fault on the system, we say that the superconductor stops being superconducting, and so I think the basic gist of the question here is that, how does that impact the cable? So when there's a fault on the system, and fault current runs through the cable, it stops being superconducting, becomes resistive, and that limits fault current. But you're correct; it also generates heat. So we have to design our systems so that there's enough thermal capacity in the wire, in the liquid nitrogen, in the design of the cable, so that the fault won't damage the material. So it's the same thing that you have to do with conventional copper cables, right? You have an understanding of what the fault current in the area is. You have an understanding of how fast the system protection is, both primary and backup, and you design your system so that it can withstand the worst case fault for the worst case breaker clearing times, and there's some standards about how often that has to repeat itself and in what period of time, and you design the system to survive that. Let's see, can we use these cables for subsea for offshore wind applications? So yes, there's a lot of interest in that, particularly in the DC realm. So our presentation was talking about AC current, but superconducting DC cables have been demonstrated. LS Cable and KEPCO, again, demonstrated a plus or minus 80 kV DC, high voltage DC cables. And there are a couple of companies that are popping up that are very interested in exactly this application of offshore DC grids using superconductor cables. One colleagues of ours, Supernode, based in Ireland, is currently digging deep into this technology and looking to develop it. I believe they just recently, in the last few days, received a certification from DNVGL that the concept of subsea superconductor cables is feasible. So that's kind of some exciting news in just the last week in the superconducting world. HTS will eliminate the use of HV transformers in the future. Yeah, so that's the AMSC project, the project in Germany. The basic idea of because high voltage transformers and cables and things are relatively large, if you can keep that equipment outside of the urban core in the suburbs where there's more room, and then bring power into the urban core at medium voltages, substations become quite a bit smaller. A rule of thumb is a substation that is only doing medium voltage is about 25% the size of a full transmission and distribution substation. So that is absolutely the concept that they're testing over in Germany. Well, not testing, they've demonstrated over in Germany. Let's see. Does the bending radius, so like all cables, all power cables have bending radius requirements, minimum bending radius. Same thing with superconductor cables. Like most cables, they have actually two different bending radiuses. One is for pulling the cable. So if you're pulling around a corner, there's a sharpness, a maximum sharpness or minimum bending radius around a corner that you can pull. And then there's a sharper or smaller bending radius at accessories. So if you're bending into a termination or bending into a splice, you can bend it more sharply than you can if you're pulling it around the corner. But they're all very compatible to or comparable to conventional cables. Condensation in the termination. So it's a very cold device. You'd be worried about condensation. So at the terminations, you're completely encased within the cryogenic or the cryostat. So there is no area on the termination that is physically cold, exposed to the outside world. At the cooling systems, often there are parts of the cooling system that does have some exposure to cold portions of the components are exposed to the air, and you do get some condensation buildup. but the manufacturers of those cooling systems have methods to deal with the condensation. Detroit Edison. So Detroit Edison was a superconductor cable project in 2001 that American Superconductor did, so 20 years ago. There was a failure in that project. So that project was using a concept called warm dielectric. Our current cables are cold dielectric cables, meaning that the electrical insulation is kept cold as well as the superconductor. 20 years ago, the industry was debating between warm dielectric, which would imply that the electrical insulation is warm and only the superconductor is cold. So your cryostat was inside the electrical insulation. The experience at Detroit Edison was that approach turned out to be quite difficult, and the cryostat failed. So that the two major things happened. Our partner in that project was Pirelli Cables, and they decided that they had enough with the technology at that point. But we were able to determine that cold dielectric cables was the more reliable approach, and the entire industry has moved in that direction since that project. So that was 20 years ago, right after I joined American Superconductor, that we had that project. What about fault events where the cable has resistance? Would the cable have the ability to expand during those events? So this question is in relation to my comment that the superconductor cables don't experience warming and cooling in a thermal cycling manner. So every day when current increases through the cables during the day, decreases at night, there's not the thermal cycling that would occur with a conventional cable because we're cooling the cable. But the point that is being made here is that when there's a fault on the system, it would warm up a little bit, and would it expand at that point? So during a fault, we do try to limit the temperature rise on the cable to about 6 degrees Celsius or 6 degrees Kelvin. And at that kind of temperature change, you don't see a significant change in the expansion of the material. It should be pointed out that when the cable is cooled down, it does contract. So we're going from a conventional, nominal temperature, room temperature when we install it, and then we have to cool it down to the minus 200 degrees, and it does contract. So we have a variety of methods to deal with that thermal contraction during the cool down. But one of the advantages here is that once it's cooled down and operating, it doesn't move anymore. So there's a whole series of topics under the realm of superconductor cables about dealing with the thermal contraction, which certainly is a different topic. If the splices are paved over in a cable failure, how is the repair facilitated? Yes, yeah, you can pave over the splice, but don't forget where it is. Right, you definitely need to remember where your splices are. So as far as damage to the cable goes, you can repair a cable segment. So if someone were to dig into a cable, you could go in, you could cut out the damaged section and splice in a clean section, and then repump the vacuum. So obviously when you damage a cable, you're damaging the vacuum in the cryostat. So you have to repair the cable, and then you can pump the cryostat back. So the cryostat has pumping ports periodically along the cable as well as at the joints and terminations, and so you have to reestablish that vacuum. More practically in urban areas, if a cable is damaged, it usually means that you pull that cable section out, and then you put a new cable section in, and you replace it splice to splice. So that would be that's what ComEd has told us, that in the event that they had a failure, they would replace the cable segment rather than try to repair the cable segment. Their comment is ComEd doesn't damage their cables. It's usually the road crew or the gas crew or someone else that damages the cable. And if someone else is paying for the repair, they want a new cable, not a fixed cable. Let's see. Thank you for the comment, Stephanie. Can existing pipe type conduit installations be directly used for superconductor cables? Yes. So if we're building a new cable, we'll generally want a 10-inch conduit for the new superconductor three-phase cable, which is a large conduit. 6-inch, 8-inch, even 4-inch is a bit more common. And we can design the cables for smaller conduits. So there's trade-offs in all things. If you go to a smaller conduit and you go to a smaller cable, that means you can do a shorter run between cooling stations. You might have to operate at different pressures and so on. And it does increase the cost of the cable to try to squeeze it into a smaller conduit. What we really think of when we're talking about replacing pipe type cable is to put superconductors in parallel with those pipe type cables. Because the superconductor cables can be relatively easily installed compared to conventional cables, installing them in parallel while the existing pipe type cable is operating is a possibility, and that has a lot of advantages. You don't have to take the cable out of service, so while you're installing the superconductor cable, you're not risking the reliability of your grid by taking the existing cable out. And then pipe type cables, no one really knows what the ultimate lifespan of a pipe type cable is. A lot of them have been operating for 50 years just fine. So just because you want to move away from the technology in time doesn't mean that you necessarily want to just go around and rip them all out. And so by installing the superconductor cables in parallel with those pipe type cables, so that when you do eventually move away from them, you can then rely on the superconductor is an approach that we're talking to a number of utilities with. OAC is saying it would seem that in order to bring additional transmission capacity to distribution systems by providing connectivity between load serving stations, unless a new transformation is added. So you're right. The idea is that we can move the transformation out of the urban core, the transformation out of the urban core and into the suburbs. So you still need transformers, right? Bulk power is going to be brought to the city at high voltages, and it still needs to be transformed down to distribution voltage. But the idea is to do that out in the suburbs or someplace where you have plenty of space for all that equipment, and then bring the power into the urban core at distribution voltages. And that's trying to be the advantages that we're trying to achieve with that concept. Let's see, Sid Zerbo is asking, how do you see such HTS cable applications with major utilities and for major transmission lines like in Quebec? So Quebec has the Montreal obviously has the same urban challenges that Chicago or other utilities would have, where we could do things like that. The other thing that Quebec is kind of known for is very, very long DC lines. High voltage DC lines. There's a tremendous amount of hydropower in northern Quebec, and moving that bulk power down into the southern parts of Quebec, and then I believe Quebec would love to sell that hydropower to the U.S. Superconductor cables in the HVDC world could potentially play that role. Whether price points of the material are competing against long distance conventional HVDC at this point is still a bit of maybe a question, but that would be the type of application I could see in that territory. But today, I think we would focus on the urban applications in Montreal and maybe Quebec City. OAC is asking, by losing power transformation at one of the stations, the associated load could only be served from the other connected station. Oh, this is going back to the question about the transformation. Yeah, again, add the transformation out in the suburbs where you have plenty of room, and then bring the power into the urban core at distribution voltages, and from there, you can go. You can help with capacity and reliability. Got some RPI fans. Let's see. What would be the lead time for the different components of the superconductor installation on average? So one of the key questions on that aspect is whether you're purchasing a superconductor cable that's identical to another one that we've installed someplace else, so that we can skip the type testing. So for those of you not as familiar, every time a new technology is put out on a power grid that has a different characteristic, whether it's a current rating, voltage rating, BIL rating, a variety of different parameters. If it's different, most utilities will require a type test, and that means that you manufacture 40-meter cable, splices and terminations, and then you test that to make sure that it meets the specification of that cable. And not until you're done with that type test can you go into manufacture the actual cable. So that can add 6, 7, 8 months to a project. So today, if we're talking to a customer that's interested in these projects, we are talking about 18, 20 month kind of lead times for these projects. But keep in mind, these are big projects. The utility planning cycle is 5 years often. So in that context, we're able to kind of supply what at a time frame that's useful for utility purposes. Rusty is asking, can you comment on the impedance characteristics differences of superconducting relative to conventional cables? Yeah. So one of the ways. So how do you calculate the impedance of a cable? So you have an inductive component and a resistive component. So the resistive component is 0, but in most cables, it's really the inductive component that dominates impedance. And the way one of the things that goes into how inductance is calculated is the distance at which the phases of the cable are separated from each other. So the closer the phases are together, the lower the inductance. In a superconductor cable like the ones we were looking at, the medium voltage cables, the phases are literally on top of each other, right? Phase A, B, and C are right around each other. And what that means is that they're as close together as you can get. And that means that superconductor cables are relatively low inductance in addition to being 0 resistance compared to conventional cables. And yeah, that does mean that you have to take that into account with system planning. The X component, the inductive component of the cable, is lower. If that's a problem, you can always install cables in series with series reactors or something like that. But generally, lower inductance is not necessarily a bad thing.
Hey Mike.
Yeah.
For the DC, the inductance is gone, right?
No. Well, okay. So
more or less.
Talking about inductance in the AC world versus the DC world is a little confusing. So in the AC world, we're concerned about inductance from a reactive power voltage control kind of standpoint that doesn't exist in the DC world. In the DC world, you're worried about inductance when you start talking about things like breakers. How does a breaker interrupt a DC current? The inductance of the DC circuit becomes a big deal, and in that kind of concern, superconductors would be identical to conventional cables from a DC inductance standpoint. So yeah, it gets a little tricky talking about inductance in the AC world versus the DC world. So Sean asks, what's the highest voltage cable rating you can currently produce? So to be clear, American Superconductor supplies the superconductor wire, not the cables. The cable manufacturers supply the cables. And LS Cable, I know, is actively marketing 154 kV. Nexans, I believe, is definitely doing 138 kV, and I know they printed a paper at, I think, 400 kV. I think they had a paper on that. Then I know there's a couple other manufacturers operating at the 115 kV world. Now, the thing is that when you get to really high voltages, and you start talking about 4,000 amps at 500 kV, that's 4 gigawatts of power. And that's a lot of power to put in, a lot of eggs to put in one basket. And we don't expect that a lot of utilities are going to be interested in 4,000 amp 500 kV or 345 kV equipment, just because it's such a large amount of power in one component. And in the utility world, you always have to be worried about what happens when you lose that component. and that's an issue. Could you please give some few supplier names of double-walled stainless steel jackets? So Nexans is the main supplier. Our cable partner also does the cryostats for us. In the industry, these are called vacuum jacketed pipes or VJ pipes. So if you Google vacuum jacketed pipes, you'll find a number of suppliers will pop up. Let's see. In the diagrams for phase concentric cables, I don't see any reference to neutral configurations. Okay, so yes, actually there is a neutral. So that is on the outside of the cable. You'd have to look a little bit closely, but both those cable designs did have a copper neutral. So like any cable, you specify the cable to be able to carry a certain amount of neutral current, and that's related to the current unbalance on the cable. Oh, you're not dumb, Sean. It's okay. So that neutral current. So if you have a 5%, 10%, 15% unbalance that you specify the cable, you then specify the size of that neutral to handle that. So the neutral is in copper. So neutral current does generate heat within the cable. So we do have to account for that. I should also point out that the neutral is bonded to the cryostat. So both the inner and the outer wall of the cryostat is included in the neutral circuit. So there's a lot of material there, but it is definitely an important specification of the cable. So I think I caught up, Paul, on the list of questions.
Yeah, so I think we answered all the questions. For those who might be interested to hear more at this topic, I think you will be back with us on January 7th. Is that true, Mike, to talk about the ComEd project?
Yeah, I think we're still making sure that everybody is free and available to do that tech talk. But I do know that some of the folks at ComEd, engineering managers at ComEd that are very close to the project, have indicated a willingness to do a tech talk about the project. And I think that'd be great to hear from the customer, from the utility, and be able for people to ask the utility engineers themselves questions about the technology and not just hear from the manufacturer.
Yeah, so maybe not 100% sure, but we'll aim for the 7th of January for that. So I think that just about completes it, Mike. I was going to announce our next Tech Talk session number 32 will be discussing ABB's VD4CS, which is a transient-free breaker that we're currently using in the renewables industry. It offers a lot of advantages in this area. It's a key device, and any capacitor bank, harmonic filter bank, is the switching device. So we will have with us next week ABB to discuss in detail that switching device, and also we will do a factory tour. We will walk out to our factory and show that VD4CS installed in our equipment and how it works there. So it will be an interesting tech talk next week. So Mike, I think we are finished for the day. We will see you back here hopefully on January 7th.
Thank you, Paul, and thank you to everybody who joined us and watched the show. Please feel free to reach out to us. We have contact information available on our website, amsc.com.
Great. Thanks, Mike. We'll see you. See everyone.